B such that the size of A is M by N and the size of B is P by Q, if and only if N is equal to P. So in other words, the number of columns in A is equal to the number of rows in B. And that would be computed by taking the dot product of the if you want element I comma j of matrix of the product of matrices A and B, you find that by taking the dot product of the row I of A with the column j of B. So, for example, finding this cell would be done by taking the dot product of this row and this column. And dot product, of course, is when you multiply corresponding components of the vectors and sum those products. So, yeah, that was previously.
So would that mean like the top one would be 2, 10, -9, and then you add those together, and then the same thing with -1, 0, and -8.
Yeah, that's right. I mean, if you want, we can do problems at the end.
Okay.
I was thinking this is pretty basic, so we don't need to go over it. But I think let's do one of these problems at the end.
No. I was just getting confirmation. I just wanted to, because someone showed me the table method, and so that was like a real good shortcut for me.
Okay. Yeah. I mean, whatever works. Yeah. I think she told us. My professor told us in class that there are multiple methods of doing it. Whichever works for you. You should use whatever you're most comfortable with. This is one way of doing it. Taking the dot product of the row and the column. That's just one way of doing it. Okay. So yeah, that's how you find an individual element of a product. The column, if you want to find a whole column of the product, you take the matrix, you take the first matrix and multiply it with the column of the second matrix. Someone's unmuted. Okay.
Yeah, I unmuted myself. There was a plane going by. Sorry.
Okay. Do you have something to say?
No, I just didn't want it. I wasn't sure if the plane was like making noise or anything like that. Go ahead.
Okay. Yeah. So row, if you want to find the row of a product of two matrices, you take the corresponding row of the first matrix and multiply it with the column, with the entire second matrix. These are just some shortcuts. And so these help you find specific elements quickly without having to do the entire matrix multiplication. An elementary matrix is a matrix that can be obtained from the identity matrix using exactly one elementary row operation. For example, here you can get this matrix from the identity matrix by swapping rows 1 and row 2. A row operation can be associated with a single, well, an elementary matrix can be associated with a single elementary row operation. For example, R1 plus K R3 would be associated with a elementary matrix. Actually, there's probably a better example. Maybe not. Oh, right here. R1. If you want to swap R1 and R3, take the elementary matrix. Take the identity matrix, perform that operation, and that elementary matrix would be associated with that elementary row operation. Or if you want to take R3 minus 2R1, perform that operation on the identity matrix, and that resulting matrix would be associated with the elementary row operation R3 minus R2 R1. This is probably getting into 2.4. So should we pause and do problems?
I have one question before we do that. Do you mind if I ask it?
Yeah, sure.
Alright, so this one is entry matrix. So
I can't hear you. There's a lot of background noise.
Yeah, there's a lot of static.
I think someone's unmuted. I'm not sure who it is. Well, anyway, my question, it was about the elementary matrix. So I was wondering, every time you do like a row operation or like when you reverse something, is that when do you have like a separate elementary matrix for each time you do a transformation?
Yeah, each individual elementary row operation is associated with a unique elementary matrix. So for example, R2 times 2 would not give you the same elementary matrix as R2 times 3. And if you want to combine two elementary row operations, you take two different elementary matrices and you'd multiply them in a certain way to get a new one.
Okay, so if can you go back to the elementary matrix a little bit before? The one with the -2. Yeah, right here. So so what I'm understanding is like with part B, because you like reversed the first and third row, is that so you also reverse the matrix from the ones being in the diagonal to the right to like switching it? Is that what happened? Like because you reversed some rows?
What was your question?
Like so for part B, since you reverse the rows, you reverse the placement of the ones. Is that what happened?
Yeah, you're swapping the rows. So you're moving this one, or you're moving the one that was here over here, moving the 0 that was here over here, the 0 that was here over here.
Okay. And then for part C, because you subtracted 2 of row 1, that's why there's a -2 in the last row?
Right. So this used to be a 0, and so now you subtracted 2 of these, so it's -2. This used to be a 0, you subtracted 2 of these, now it stays a 0. This used to be a 1, you've subtracted 2 of these, so it stays a 1.
Okay. And then, so you just said that if you're combining two row operations, you multiply their elementary matrices? Is that what you said?
Right, yeah, but the order matters. I think
Yeah.
we'll get to that later, or maybe that's not part of this exam. I'm not sure.
Okay. Well, I just want to confirm. So thank you.
Yeah, no problem. Should we move on, or should we do problems before we get into 2.4?
Down to do a problem or two.
Okay. Okay. Problem 1 from the textbook.
Sure.
Okay. Let's take like 5 minutes to do all three parts.
Yeah, that's fine.
Okay. Cool.
Where can we find the questions?
This is the textbook, section 2.3, problem 1.
Oh, okay.
You can also go to notes and resources to ps4.pdf, and it's in there.
Which one did you say in notes resources?
It's called
Yeah,
or PDF.
Got it. Thanks.
so just real quick, A would be
We'll go over the answers in a few minutes.
oh no, I
I don't
just
even
wanted to
understand what
ask.
it's asking.
Yeah, I just wanted to ask this one little quick thing. Subtracts 5 times row 1 from row 2, so it'd be R2 minus 5 R1.
Yeah, R2 minus
Okay.
5 R1.
I have a quick question.
Yeah.
Okay, so I was just looking through this and doing it on my own, and I was just like wondering, if a question like this was asked on the test, like, because it doesn't really take a lot of work to do it. So would it be okay to just like write the elementary matrix and maybe like include like 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 if it said subtract 5 r row 1 from something, like would it be okay to just write R1 minus R2 or whatever it might be, and then just write the matrix, like, because it doesn't look like you need a lot of work to do it.
Yeah, I mean, that's probably what I would do. I might
Really?
write the original, I might rewrite the original matrix, and then, I might just like be very nitpicky about showing all of my work.
Okay, yeah, I was wondering about that too, because it feels like there's not much to write down, so I don't know if maybe there's something else we need to do in between, or
There's no
if we
work
can.
for this problem, right?
Yeah,
Yeah.
not very. There's very little, especially since we're using the identity matrix.
Yeah. Okay.
Okay,
Okay.
we
Thank.
should we can go over it now.
Yeah, let's go over it.
Yeah, because I don't think I wrote down the right stuff. It seems simple. I just don't know what it's asking.
Okay, so here's the identity matrix for just for reference. So for part A, we're asked to subtract 5 times row 1 from row 2. That's row R2 minus 5 R1. And so we leave, first of all, we leave R1 alone. We leave R3 alone. With R2, we subtract 5 of each component from the corresponding component with row 2. So since we have a 1 here and a 0 here, we take 0 minus 5 times 1, which is negative 5. 1 minus 5 times 0,
お
0
願い
minus
し
5
ま
times
す。
0, and so on. And then for part B, we leave the first row and second row untouched because we're doing row 3 minus negative 7 row 2, which is row 3 plus 7 row 2. And so these two cells are unchanged because row 2 has a 0 in those columns. This cell is incremented by 7 because there's a 1 in column 2 of row 2. And then for part C, we first swap row 1 and row 2. So this becomes 0, 1, 0, 1, 0, 0. And so since that's all we're doing with row 1, we can write that as our final matrix. We can write row 1 as we can write this new row 1 as the row 1 of our final matrix. But since we're swapping row 2 and row 3 again, we have to perform the swap. From 1, 0, 0, we get 0, 1, 0, 1, and then we get 1, 0, 0 for row 3.
Makes
Does that make sense?
I was getting confused because I read the solutions.
Oh, I should check the solutions.
It's all good. I was like, I thought we got the solution. I didn't see that it said solution, so I thought it was part of the problem. I was like, what are we doing? But now I
Oh
get
yeah.
it. We're good.
Okay. Yeah, I mean, I should probably make sure my answers are right before presenting them. Okay.
They match the solutions. You got it.
What was that?
They match the solutions. You got it.
Oh yeah. Problem 3. Oh, by the way, I guess this expects us to know it, but here I'll just cover it from the notes. The elimination matrix is what you get when you multiply M, the equation for a system of equations, or the matrix for system of equations. The elimination matrix is what you get when you multiply that and the matrix, such that the answer is an upper triangular form. So in our case, that's going to be E1. We're going to call it E1, E2, E3. And the way you does it not talk about it? Oh, it's probably later, but the way you like associate row operation, like groups of row operations with matrices is by performing by multiplying the matrix by the elementary matrix to the left. So for example, if you want to multiply well, if you want to perform this operation, R2 R3 plus 7 or R2 on this matrix, you'd take this matrix and multiply it with this matrix, but this one would be on the left because this is the second operation, if that makes sense.
So when we have elementary matrices, we multiply them from the left side, basically.
Yeah, if you want to perform the operation associated with this matrix to this matrix, then this matrix will be on the left.
Gotcha.
Our professor called it pre-multiplication. Yeah. I'm not sure if this is relevant, but she told us that would give you column operations instead of row operations. But yeah, so just like if you want to, I mean, with elementary row operations, all you really need to know is that you multiply you put the elementary matrix on the left. You put any new elementary matrix on the left.
Could you say again what makes column operations?
Yeah, so if you put this is an elementary matrix, right? If you put this elementary matrix on the right of this matrix, you'll
Oh.
perform this column operation. So which would be column 2 plus 7 column 3.
So we put row operations on the left side of the matrix.
Yeah. And
Yeah.
since we're only dealing with row operations for most of linear algebra, we pre-multiply or multiply with on the left.
All right, thanks.
Yeah. So that's going to be useful for problem 3, which means which asks you to perform 3 elementary row operations on A to get it to upper triangular form, and then write down the matrix or the 3 different matrices that will get you there. Let's take like
I got one question.
Yeah.
Okay, so because I kind of got confused with that on the homework, so I just want to make sure. So when we say like, for example, if you say like row 1 minus row 3, the row that's getting modified or like transformed is the row that you write down first, right? So if you say row 1 minus row 3, row 1 is being modified, and row 3 is left alone, right?
No, I'm not really sure. That confuses me all the time as well.
Okay, yeah, because I don't know if like when if the order for that, like sometimes like reverse order, I don't know if I'm writing it wrong.
It
Yeah.
doesn't. The order does matter. I'm not sure. Well, the textbook says row E21. It doesn't say E12. You never eliminate row 1, right?
I
Yeah,
think
yeah,
the
yeah.
first digit is the row that's being acted upon, and the second one is what's doing the acting. But
Okay.
it doesn't say the multiplier in it. That really confused me in my lab section, but my lab instructor didn't really give me a clear answer. So I think it's not included in the notation. You just have to like know it in your head.
Okay, okay.
Okay.
In this problem, they're basically saying, hey, figure it out based off of like these. It's also to help you get the order right because they want you to do
Yeah, and also like you usually don't eliminate a lower numbered row with a higher numbered row. Like you don't use your row 3 to eliminate something from row 2
Yeah,
for
yeah.
upper triangular form.
And then like also for matrices, I was wondering. So when you say upper triangle, that means all the zeros below the diagonal are all 0. And then when you say lower triangle, all the zeros above the diagonal are 0, right?
Yes, but the textbook says for lower triangular form, the diagonals must all equal 1. It places no such restriction on upper triangular form.
Okay.
Okay. Yeah, let's take like 5, maybe a little bit more minutes to do number 3. Okay, should we go over it?
Yeah.
Okay. Okay, so yeah, we want to get this system into upper triangular form. So first we eliminate this 4 by performing R2 minus 4R1. Then we want to eliminate this 4, this negative 2 by performing R3 plus 2R1 to get 0 here. Then we want to eliminate this 4 by performing R3 minus 2R2, and so we get a 0. And now this matrix is in upper triangular form since every entry below this diagonal has a 0. And so the matrices associated, the elementary matrices associated with this this transformation, I guess, will be this matrix E21, which would be associated with R2 minus 4R1, E31, which is associated with R3 plus 2R1. I'm not sure if this is correct, actually. Let me change this. So yeah, this is better. It should it be negative? No, it's not. That's right. And then E32, which is associated with R3 minus 2R1, R2, right here. And so if you multiply these matrices together, this one times this one times this one, in that order, and then you or not in that order, sorry. This one times this one times this one, and then you wait. I'm reading this wrong. Okay. You perform this operation first, which means that when you multiply this one by this one by this one in that order, then you multiply this by the original matrix A, you'll get an upper triangular matrix, which is this. So this this matrix times this matrix times this matrix times this matrix will give you this upper triangular matrix.
Yeah.
Yeah, to upper triangular, yes. And then, yeah, the order definitely matters. Yeah, because let's say you well, let's say you do this one before you do this one, you'll get a different answer from when you do this one before you do this one, because both of these let's see, one of these affects row 2, one of them does not affect row 2. Does anyone have any questions on that?
I don't think so.
Okay. This one's fairly straightforward. I mean, I want to get to some hard problems.
I agree. Augmented matrix is good to know, but it's pretty simple. I think we've covered it in class several times.
Oh, by the way, yeah, matrix multiplication is associative, but not commutative. So,
Grouping doesn't matter, order does.
So multiplying A by B is not equal to multiplying B by A. However, if you group two matrices, like if, for example, AB times C is the same as AB times C is the same as A times BC. And there are there's a whole bunch of like other properties, but those two are like the most important ones. And you can use those two properties to derive the others. Okay, let's do 27. Let's take like 5 minutes to do 27. I think this will be on the exam.
Are we doing 4?
No, we're doing 27.
We
Oh.
skipped to 27.
Okay, should we go over it? Okay, so looking at the final equation, if we set d to anything but 0, we should get one unique solution no matter what a, b, and c are. No matter what a, b, and c are, we'll have one unique solution. So therefore, we're looking for cases in which d equals 0. So if we let d equal 0, then if c equals 0, we'll have infinitely many solutions because we'll get 0x plus 0y plus 0z equals 0 for d and c equal to 0. And with that, and no matter what a and b are, you'll have either an infinite plane of solutions. If you let d equal 0 and c not equal to 0, you'll get no solutions because you'll get 0x plus 0y plus 0d or 0z equals something that's not equal to 0, which is never true no matter what a and b are, no matter what x and y and z are. And so the answer to this problem is, for there to be no solutions, a, b, and c can be anything, and d is anything but 0. Or sorry, for no solutions, a and b can be anything, d equals 0, and c can be anything but 0. And for infinitely many solutions, a can be anything, b can be anything, but c and d are both equal to 0. Does that make sense?
The part about A and B being anything, is that just because it's like triangular, the way it pans out?
Yeah, it's because it's upper triangular.
Even with 0? I guess that would work too.
Yeah.
Okay.
Yeah. This really only works for an upper triangular system. So if you get to a successful point where like d is not 0, or d is not 0, and you get like something like, I don't know, 2z equals 4 or something, you're guaranteed a solution.
Gotcha.
Yeah, I don't like the way it was written. I'd rather have, if I want to see an augmented matrix, I'd rather see a bar with it.
Wait, so let's say D is 5. Is there any value of C where there's no solution or infinitely many solutions?
No, because D is in the pivot spot, and the pivot spot is not equal to 0.
But
D
let's
equals
say,
5.
I guess, but wouldn't there be infinitely many solutions? Because if D equals 5 and C equals 0, wait, no.
No, you get 5z equals 0. So
Mm-hmm.
z equals 0.
Okay.
Does that make sense?
Yeah.
Okay. Should we do 25? I feel like that's probably going to be on the exam as well. I don't know, maybe. I'm guessing the answer to this problem is like you're gonna have to, like, without looking at the answer, I think the answer to this problem is like you're gonna have to eliminate rows 2 and row 3. You're gonna get a 0 either here or here, and then it'll be no solutions. You'll get like 0, 0, 0, and something but 0 here, right? Yeah, right there. That's the only way you can have a system with no solution. Let's move on to 2.4. But before we do so, are there any questions on section 2.3?
Actually, I think I'm a little confused about like what 21 was asking while I was just looking through it.
Okay, 21.
Yeah, because it was giving like, it was talking about EF equal SE, and it's using like the previous matrices, but I don't know why
Oh,
it came from like a 3x3 to a 2x2 in the solution.
no, I think these are generic matrices E and F. I think these are elementary matrix, any random elementary matrices E and F. No, they are associative. They're not commutative.
Oh, so it's just like a general question then.
Yeah, it's for
Oh.
yeah. Actually no, because sometimes I mean matrices it's not guaranteed to be non-commutative. I mean I'm not sure if that's even possible to guarantee for any like operation, but it's not that you can't switch the order and get a right answer. It's that switching the order of two matrices when you're multiplying them does not guarantee the right answer. For example, if you multiply like matrix A by its inverse, A times A inverse, and if you do A inverse times A, you're switching the order and you're still getting the same answer. So therefore, like therefore it is possible to find two matrices such that their multiplication is commutative. However, it's just in the general case, you really can't make that assumption. Does that make sense? Okay. Yeah, let's move on to section 2.4. Yeah, this is just matrix addition. This is very simple. It's just like matrix. It's just like vector addition. All you do is add up the corresponding elements of the matrix. So, for example, if you want to add these two matrices, if you want to find this cell, if you want to find this cell, you take this cell of this matrix, add it to this cell of that matrix, and that's your entry for this matrix. Scalar multiplication is it's very similar. You just multiply each element of the original matrix by the scalar. Oh, right here. These are the properties of matrix addition and multiplication. Matrix addition is commutative, but multiplication is not commutative. Let's see, is that? I'm trying to see if they actually cover that. No, okay. So yeah, addition is commutative. Addition is also associative. And you can also use the distributive property. So for example, k times, it's distributive with scalar multiplication, not with matrix multiplication. So if k is a matrix, I'm not sure if you can do that. You might be able to though. Okay, right here. Matrix multiplication is not commutative. Matrix multiplication is distributive. Okay, so here, if k is a matrix, you can distribute like this. If k is a scalar, you can distribute like this. Matrix multiplication is associative, as we said, but not commutative. Block matrices. This is something that's pretty obscure, I guess. I think we can expect a question on this.
It'd be nice to do a problem over this. I don't really
Yeah,
have a good
we didn't
grasp.
even have a homework problem over this. I think it'd be nice as well. I actually don't know what this is saying. I don't remember. But basically this is a convenient way to like break down a matrix multiplication into smaller problems, like a divide and conquer algorithm. You treat this as a matrix with 4 different cells. So, for example, this matrix with 1, 2, 3, 4, 5, 6, 7, 8, 9 would be A. This would be B. This would be C. This would be D. D would basically be the 1 by 1 0 matrix. This would be a row vector. This would be a column vector, and this would be a 3 by 3 matrix. And so this is really useful when you're doing block multiplication, which is when you multiply a matrix with when you multiply a larger matrix with a larger matrix, and you want to simplify it a little bit, you multiply the chunks first, and then you expand them. So, for example, this 2 by 2 block matrix times this 2 by 1 block matrix would give you a 2 by 1 block matrix. And so you can use, and then once you finish multiplying, you'd re-expand the block matrix. What that means is the number of columns in the first block matrix must equal the number of rows in the second column matrix, in the number of rows in the second block matrix. So, for example, if you have a if you have like a 4 by 9 matrix multiplied by a 9 by 5, you can't partition the first one into the first 9 into 3 by 3 by 3, and the second 9 into something like 2 by 7 or something like that. The sizes must be equal. And so here's an example of using block multiplication. Notice that this block is the 0 matrix. This block is an identity matrix. This is a 0 vector. I guess okay, yeah. So you have two blocks for the columns of A, and 2 blocks for the rows of B. And each block has the same size. Well, each corresponding block in A has the same size of the corresponding block in B. There are 2 columns per block and 2 blocks for the whole matrix. There are 2 columns per block, and there's 2 blocks per matrix for B. For you could, I'm not sure if this is accurate, but I'm pretty sure you can move this cut over here from here to here, and then move this cut to here. So you get 1 and 3 and 1 and 3. But I'm not sure if that's allowed. I'm not entirely sure.
That makes sense to me.
Okay. I think an example will really help, even for me. I'm not really sure how to do this. Oh, yeah. Here's an example of an asymmetric partitioning. You have 3 columns and 1 column, 3 rows and 1 row. That's how you're supposed to cut a block matrix. I remember her going over this in class. She said something. There was something very important about this. I'm not sure what that means. Yeah. Let's do some problems. I feel like that's a better way to understand it for me. Does anyone have any questions before we do problems?
Let's go for it.
Yeah, let's go for it. Okay, 3. Let's do 3 from section 2.4.
done with this one?
Kind of. Not really. I've been typing it all out, so it's been taking me a while. Okay. Uh, is this the right answer for the matrix? Okay. Yeah. I wasn't able to complete the matrix multiplication because I had to go back and fix an error. But I think multiplying these two matrices should give you 3, 8, 6, 9.
That's what I got.
Okay. Yeah. This proves that this is an example of the distributive property of matrix addition and matrix multiplication. Anyone have any questions? Yeah, this is relatively straightforward. This, I mean, this is number 6 is pretty straightforward as well. It's well, the proof is that matrix multiplication is not commutative, so it would be a squared plus ab plus ba plus b squared instead of 2ab. Let's do 17.
Which one are we doing now?
7 1 7. Okay, should we go over it?
Sure.
Sure.
Okay, so so if you want to find the second column of matrix A times matrix B, what you do is find matrix A times the second column of B, which will give you, and since this is the zero vector, the zero vector, anything times the zero vector is a zero vector. If you want to find row 2 of AB, you find row 2 of A times the entire matrix B, and so multiplying like each this row by each column of B, you get 1, 0, and 0. Now if you want to find row 2 of a squared, you find row 2 of a times a, all of a. Again, you do it component wise, and so that's going to give you 6 minus 6 is 0, negative 3 plus 4 is 1. And so for the final product, I guess, you notice that a cubed is equal to a squared times a. If you want to find row 2 of a cubed, you take row 2 of a squared multiplied by all of a. Notice that we find row 2 of a squared over here. So we substitute that in over here. You multiply this by row 2 of a, or by all of a, sorry. You get this. You get 3, negative 2. Does that make sense?
Yeah, it does. I was
Basically
doing
what we're using
7
is,
instead of 17, but this makes sense.
oh, yeah. Basically what we did was use, these two shortcuts, number 2 and number 3. We might be expected to know these. I'm not sure. I would have it. I would memorize it. I mean, it can't hurt to. Yeah. Any questions?
I think you can kind of remember it by like the one on the left affects the rows and the one on the right affects columns. So if you're doing rows, you're gonna like wait, I'm confusing myself. You take the row from the first one and multiply it by the second one, right? Can you pull those notes back up?
Yeah.
Trying to see if I can come up with a rule of thumb. Yeah, so that is right. So yeah, if you're going for rows, you grab it from the left, and if you're going for columns, you grab it from the right. I guess that's
Right.
how I'm gonna remember it, I guess. I think we're tired.
Yeah. Let's do like one.
How far does this chapter go? I guess most of my like confusion has come from like the latest chapter, and I guess that's not going to be on the exam or anything. So
Which one?
just like the stuff we're doing like now in class.
LU composition, all that.
Yeah, I get the idea, but I wouldn't be able to do problems. I'm not saying I want to
Right.
practice that now. I'm just
Yeah. Let's do. Well, I was gonna say let's do 26, but they basically do it for you. Okay, 32.
32. Okay, very important.
Oh, it's pretty easy. Or wait, never mind. Never mind, it's not easy.
I think it might be. I don't I don't get what all the setup is for. tells you to put together the identity matrix column by column, then asks what a matrix times the identity matrix is.
No, that's what I thought, but no, you're not. You're not putting together 1 0 0 0 1 0 and 0 0 1. You're putting together x1, x2, and x3.
Oh, let me think about that then.
Okay, I'm actually pretty close to solving this. I'll need some time.
$32.
Yeah.
Oh, okay.
Okay, I just solved it. I did it on paper, but basically, AX will give you the identity matrix.
I think another way to look at it is in order to get those results, basically we know that X is effectively slices of A inverse, because otherwise it would be impossible to get like that configuration pretty much. And I guess if you look at the solution, I guess what they're testing us on is whether or not we understand like the distributive part of it, which is kind of weird because they don't show any other work other than the distribution. So I wonder if that's what this question is about.
I'm not sure. I did it like the brute force way. Like
Oh,
I
you like did every value.
yeah. Well, kind of. I did it the matrix multiplication way. I think the best thing I can do is just upload a picture of what I did.
Sure.
I think it's also trying to show, like, if you do A times the first column, then that would be, like, the first column of A times X. So it just wants you to, like, combine the columns.
Yeah, I agree.
Okay, yeah, I put my solution in a session plan. But basically, x1 would be A inverse times 100. X2 equals A inverse times 0, 1, 0. x3 equals A inverse times 0, 0, 1. And so the x1, x2, and x3 are just columns with certain cells of A inverse. And so the matrix X would just be a row vector of these columns, which means X is the cells of A inverse, which means X is just A inverse. And so A times A inverse is just the identity matrix.
See,
That's like the full, like, I guess that's the more proper way to do it without taking any shortcuts.
yeah, you did a very rigorous way of doing it. Yeah, showed it pretty well. I guess, I mean, what we do end up with, like, whether you like do it from the bottom up or whether you do it from the top down, you pretty much
Right.
find that. Like X is just slices of A inverse, and you prove that by calculating each slice of X pretty much.
Yeah.
I do wonder, like, if, you know, how much time we're gonna have on the exam, because these problems aren't short, so I'm worried that we're gonna have like 5 problems and they have to be perfect. You know, that's
Yeah.
what I'm worried about.
But yeah, that's all we have for recommended problems.
Right on. Well, I guess I'll go back and see what stuff I missed. Catch back up. It's a good
Yep.
thing we don't have homework due this week, but the homework for
Yeah,
next
that'd be
week
too
looks rough.
stressful.
Got a couple of days. Do y'all work on the homework? I know some of y'all like do like a thing at the library, or at least used to. Would y'all be interested in going over it like online, maybe in separate groups? Because I know y'all like that Saturday time slot, but I'm busy then.
I don't know what you're talking about.
Intriguing. Oh, okay. I know some people met up on Saturday to work on the homework through here. And I was never able to join because I'm busy on Saturday. So I was just wondering if that's still a thing that happens. But it's no biggie.